The diagram below shows the energy levels of a hydrogen atom. Calculate the ionization energy of an electron which is in its ground state. So it's here n equals 1, and to ionize we need to remove it completely from the atom. So basically we have to send it all the way to n equals infinity. So there the electric potential is defined as 0, and here it's 13.59. So actually what we'll need is that whole 13.59 to send it. That's the minimum energy we'll need. If we have more, that's fine, we'll come out with some kinetic energy. So the minimum energy, ionization energy, is 13.59, and you can turn it into joules and you get this answer. Okay, an electron is excited to the energy level n equals 4. Determine the number of different photons that can be emitted from the de-excitation of this electron back to the ground state. Okay, it can come down in multiple different ways, okay, going through different intermediate energy levels. So to count these without losing track is you should count all the possible routes from each energy level. So for example, from this one, the n equals 4, you can come down here, or you can come down here, or you can come down here. And then let's go move on to the n equals 3 and count the different ways from there. So you can come down this, or you can come down here. And finally, from n equals 2, you can go from here to here. So the total different possible energy gaps, and therefore the different photons that can be emitted, is 1, 2, 3, 4, 5, 6. So 6 possible different photons that can be emitted. Okay, a free electron with a kinetic energy of 12.3 electron volts collides with this atomic electron in its ground state. Determine the highest energy level the atomic electron can be excited to. Okay, so it's got 12.3 electron volts. So if you want to go to the first energy level here, it will need to absorb 13.59 minus 3.4. So it'll need 10.19 electron volts. And the free electron does have that much energy, so we can go to n equals 2. That's fine. Let's try to go from here all the way up to this point here. To do that, you'll need 12.048 electron volts. So that's fine. We can go to this because the free electron can provide that much energy. But let's try the next one here, n equals 4. So for that, the difference there is 12.74. So that means we can't go there because that's more than 12.3 electron volts. So it won't be able to make that transition. Okay, an electron in its second excited state, basically n equals 3, de-excites back to the ground state. Calculate the longest wavelength photon that can be emitted during this process. So there are 3 possible ways it can come down. Okay, just using the same method I drew before. These are all the possible transitions. And using the energy of photon equation here, we want to find the photon with the longest wavelength. That actually means the smallest energy gap. And the smallest energy gap, and you'd have to actually calculate the number yourself, is this one here between these two. Okay, so that energy gap corresponds to 3.40 minus 1.51, and if we turn that into joules, here's the energy gap, and then I'm going to put that into the equation for the energy of a photon. There got Planck's constant times the speed of light divided by the wavelength. Bring the wavelength to the other side and the energy down, and that gives us a wavelength of 358 nanometers. Basically, red light will be emitted during this transition over here.